Okay, here we go.
In The Hobbit was hilarious.
Is it recording now?
It's recording, Bob, and no, Ross. I have not yet seen The Hobbit.
Oh, you should.
Okay, well, Gollum's part is like the best part.
Hello, John.
The rails part?
Hello, Melanie. Hello, Corey. Hello, Michael Becker. If you're watching this, that's awesome. If you're not, I guess that's awesome too. But anyway, we're here. We're going to go through problem 2002 from the Physics B test, Form B, and it's problem number 5 from that test. But anyway, it's the one that has the parallel plates with the E field in the middle. All right, so it tells us...
There's a lot of problems like that.
There are a lot of problems like that.
So I don't know, which is this the one where it's like 5,000 newtons per coulomb in between?
Yes, Bob, it is. Now, it tells us that the plates are separated by a distance of 2.0 times 10 to the negative second meters. It also tells us that the area on the plates, on each of the plates, is 0.3 square meters. It also tells us that there's a charge Q on one side and a charge Q on the other. So I'm going to say plus Q, oops. I'm going to say Q here, and I'm going to ignore the sign of those charges just now because one of the problems asks us that. Okay, so it tells us the strength of the electric field is 5,000 newtons per coulomb. It says A, indicate on the diagram which plate is positive and which plate is negative. Now, as everyone should know at this point, the convention says that E field lines go out from positive into negatives. So my hope would be that you called this the positive plate, positive, 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 and this the negative plate. Which means this is positive Q and this is negative Q. And that was part A. Part A was worth a total of 2 points. And you got those 2 points if you indicated the correct polarity. So that means plus here, minus there. So plus 2 for correct polarity. Okay, part B. Question B asks, determine the potential difference between the plates. Okay. Well, they give us the strength of the electric field. And I don't know if you guys remember this at all, but another unit for electric field would have been volts per meter. And that may have been a sign that you could have looked at your green sheet to say, oh, well, let's see. E field strength equals volts per meter, Oh, E average equals negative V over D. So, for part B, you could have used that equation to say E equals V over D, and now what I'm doing is I'm neglecting that minus sign, and I'm going to pretend that the field's uniform. So what I'm going to do is, in this equation, I would simply need to solve for V. So V equals the strength of the electric field times the distance d apart, ed. Plugging in values, I get 5,000 newtons per coulomb. And then I have a distance of separation of 2 times 10 to the negative second square meters. That's, oh yeah, that's right. Oh no, what am I doing? I'm mixing up area and, okay, there. Now the reason I said that electric field also has units of volts per meter is to help me pick out this equation. So it's just one of the equations. And we'll work on some equation stuff in the future. I have an idea. Okay, so if you plug those in, you're going to end up with a value of 100 volts for part B. Now I can tell you that for part B, there were 2 points total for part B. You got 1 point for correctly substituting in values and 1 point for the correct answer. So if you didn't use this equation, but you did remember that electric field also has units of volts per meter, and then you just wrote in those numbers, that was worth a point. Ross? Well, joules per coulomb is what a volt is.
Yeah.
I think you'd get that point, but typically if they're looking for an answer for potential difference, it's going to be volts. And we'll be using that unit a lot, and I think that you'll just become accustomed to using volts.
Yeah. That's probably what it was that I just didn't make the connection.
Okay, well, that's okay, Ross. Next, part C. Part C asks, determine the capacitance of this arrangement of plates. If you remember us talking about capacitors, there's a general formula that looks like, for capacitance, I go C equals, and it's right on the green sheet. I can point it to you guys here. Right there. Can you see that okay? I hope so. Okay, capacitance would be equal to epsilon naught times the area of the plates divided by the separation distance d. So if they're asking us for the capacitance, they give us everything that we need. Epsilon naught you have to look up. It's, what is it, 8.85 times 10 to the negative 12 coulombs squared times, or divided by newtons times a meter.
Is it meters squared?
Yeah.
Yeah, there's a mistake in this rubric. They left that out. Times the area, which is 0.3 meters squared, all divided by that separation distance, which was 2 times 10 to the negative second meters, which I guess would have been 2 centimeters. But capacitance, if you would have punched that in your calculator, you would have got 1.3 times 10 to the negative 10th farads. Or, if you would prefer, I mean, you can do this, 130 picofarads. So all I did is move the decimal place over, so then it's times 10 to the negative 11, times 10 to the negative 12, and then times 10 to the negative 12 turns into pico. Or you could have gone the other way and said 0.13 nanofarads. It doesn't really matter. This works out perfectly acceptable as well. So point-wise for this was also worth 2 points. You would have gotten...
Good morning again, students. It's This time in the sophomores will qualify for having them pull up and report to the cafeteria after a slight pizza delay. But the pizzas are now here.
Is anyone a sophomore?
To the cafeteria or the honor roll first and or second.
Just kidding.
Thank you.
Oh, good one.
+1 for correct substitutions, +1 for the correct answer. So that would have been 2 points for part A, 2 points for part B, and 2 points for part C. On to part D. Part D says, oh wait, but first, somehow there's an electron initially positioned right in the dead center between the two plates. Midway, it says. So I'll put one. An electron! E. Negative. That's my electron. Determine the magnitude of electrostatic force on the electron at this point and state its direction. Okay. Well, I can tell you there's a relationship that works out pretty well. So for part D this is. I have on my green sheet, let me look there first. I have an equation that relates electric field as force divided by charge, newtons per coulomb. So I can say E field equals F over Q, and then I can say, well, that force that it's going to exist, or the force that will exist is equal to Q times E. So all I have to do is plug in values. That electric force is going to equal, the charge on an electron is 1.6 times 10 to the negative 19 coulombs, which that value...
Can't treat anything static, just like physics.
All right, Bob.
My philosophy of the day.
We had a little technical difficulties, so welcome back. I'm not sure if you guys got this, but for part D, it's asking us for the force on the electron, and I'm using this equation from the green sheet. And I was right in the middle of plugging in values here, so I'm not quite sure where it ended. We'll figure it out later. So I take the charge on an electron, the magnitude of charge on the electron, multiply it by 5,000 newtons per coulomb to figure out the force, and the force ends up becoming 8 times 10 to the negative 16th newtons. Now, that force, if it's on an electron, right, negative charge, think about this. In what direction is a force on a negative charge inside an electric field? And the answer would be opposite the direction of the field lines. Because remember, those field lines are set up by the convention that those lines are for a test charge, which is a tiny little positive charge. Okay, so we have that. This one was 2 points. You got 1 point for the correct magnitude of electric force, and then 1 point for saying oops, I drew my arrow the wrong way. It points to the right, or you could decide positive x direction or towards the positive plate. But there you go, +2 for that. And lastly, part E. Part E asks us, if the electron is released from rest at this location midway between the plates, determine its speed just before striking one of the plates. And we get to neglect gravitational forces. So, one thing you could have done is, I guess you could have done a little energy analysis. So if you said this was your situation 1 right here, when it's at rest, all the energy is electric potential energy. And then right here when it's on the plate, that's going to be all kinetic energy. So if we're looking for the speed, I could say, I'm going to go part E right down here. I could say that the potential energy U sub E in situation 1 equals the kinetic energy in situation 2, like that. And then I could say, oh, well, that's going to equal, what is the electric potential energy? Let me look up an equation for it on my green sheet. Dun, 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 dun. Q times V, right? Magnitude of charge times the potential difference, and that's going to equal kinetic energy. Well, the electron's just a particle, so I say 1/2 mv squared, and I'm looking for V. So now all I have to do is solve for it. V is equal to the square root of 2 times Q times V, ooh, that's a big V, all divided by the mass of the electron, me, because we're dealing with an electron there. Now, I know you guys can substitute those values in. The mass of the electron is a constant that's given on the front of your green sheet, but I guess I did choose a bad spot to write. I can erase C because we've already done it. I have V, the velocity, equals the square root of 2 times 1.6 times 10 to the negative 19th coulombs times, oh, but here's a question. What value do I enter in for the potential difference? Well, Matt Johnson, I'm glad you guys said that, because right now the potential difference is 100 volts between this point here and this point here. But if we're directly in the mid-center, yeah, it becomes 50 volts. So you got to be sure to pay attention to that. Now, there's an alternative solution that I'll talk about here, but 50 volts, all divided by the mass of the electron, which is it 9.11 times 10 to the negative 31st? Yes!
Right?
What?
Sounds right.
Oh, thanks, Bob. If I punch all that into my calculator, I'm going to end up with a value of 4.2 times 10 to the 6.
Yeah, I got that. I did it differently.
My guess is yes, you must have. Because, Bob, you did the same thing, too, as Michael must have done.
What?
I'm not sure. I'll go over it in a second.
Yeah, we did the alternate solution.
Oh, okay. So the alternative solution, which I'm going to erase part B. The alternative solution would be to say, oops, not, I'll call it E alt. What time does this class end? 40. Oh, I still got time. Okay, perfect. The alternative solution would say, well, I know that any force is equal to mass times acceleration, right? Newton's second law. Acceleration therefore equals whatever that force is divided by the mass. Well, lucky for us, in problem D, we solve for that force, and we know the mass of an electron. So then what I can do is I could, you know what? I'll solve for that acceleration. So the force is simply 8 times 10 to the 16th, excuse me, negative 16th newtons, divided by the mass of an electron. I don't know if you guys can hear that on the video camera, but they're being obnoxiously loud in the hallway. Just thought I'd let you know. Times 10 to the negative 31st kilograms. Boom. We're going to get an acceleration of 8.8 times 10 to the 14th meters per second squared. That is an insanely fast acceleration, correct? Do you guys agree?
Yep.
Now, but think about this, that acceleration only happens over the course of 1 centimeter. So I don't know how fast it's going to be moving at the end, but we can simply apply our, I'm going to move down here.
It's not even going to be a second.
No, it's not even, we could in fact calculate the time if we wanted. But I'm going to use this equation. My displacement, that's what this section is right there, that's simply going to be 0.01 meters. Right, that's 1 centimeter because I know there's a distance of 2 centimeters between the plates. My initial velocity is 0 and I have my acceleration. So v equals the square root of 2 times the acceleration times that new displacement, which I'm just going to refer to as delta x. Plugging values in, I have 2 times 8.8 times 10 to the 14th meters per second squared, all multiplied by 0.01 meters. That gives you the same magnitude of velocity. Boom. So, 2 ways to solve it. Both are perfectly acceptable. Let me tell you how points were awarded. If you followed this solution, you would have gotten 1 point for recognizing that the potential difference was 50 volts, and 1 point for the correct answer. If you did the alternative solution, you got 1 point for determining the acceleration, and 1 point for the correct answer. So that brings your total to 10 points for that problem. Any questions? That's it then. The end.